Hey guys, with this video we're starting chapter 3, and in this chapter we're going to start looking at certain rules that we can use to evaluate derivatives quickly. Um, 3.1 we're going to talk about derivatives of polynomials and exponential functions. So the first rule is the power rule, and I'm just going to give this to you here, and at the end of this section, probably in the last video for this section, I'm going to show you why this rule works, but for now just take my word for it. The power rule says that for any real number n, if we want to take the derivative of x to the n, what you do is you get n x to the n minus 1. The way that I like to think of this is the n sort of jumps back to the front and then you take 1 off of it. So let's, before we do these special cases, let's just look at some examples. The derivative of x to the fourth is going to be 4x to the third. So you just move the exponent down front and then subtract 1 from the exponent. Derivative of x to the 10th is going to be 10x to the 9th. Let's do one more easy one here. The derivative of x squared is going to be 2x to the first power. All right. Now, we can also do this when the exponent is not a whole number. So, like right here, derivative of square root of x, you can rewrite that as the derivative of x to the 1/2. Then we move the 1/2 down front. So you get 1/2 x to the 1/2 minus 1 is negative 1/2. So you could leave this like this, or you could move that to the downstairs and get 2x to the 1/2 there. 1 over 2 root x. I'll put a box around this since it's sort of long. Similarly, for cube root, you could rewrite that as the derivative of x to the 1/3. So that becomes 1/3 x to the 1 minus 1/3. So it's 1/3 x to the negative 2/3. And if you wanted to, you could rewrite that as 1 over 3x to the 2/3, or 1 over 3x to the, well, let's see, we could write that as x squared under a cube root. Honestly, on these, I would probably do the square root down to here, but when it gets into more complicated fractions, more than just a half, I'd probably just leave it like this. All right, let's do a couple more. Derivative of 1 over x. Rewrite that as the derivative of x to the minus 1. So this becomes minus 1 times x to the negative 1 minus 1. So that's minus x to the minus 2, or negative 1 over x squared. And this would be derivative of x to the minus 5. So that's minus 5x to the minus 6. Or if you prefer, negative 5 over x to the 6th. So once you know this rule, doing derivatives of powers is really simple. And again, this is called the power rule. Now let's go back up and look at these special cases. Derivative of x is just 1. That makes good sense because when you take the derivative of x, so let's say the derivative of x to the first power, that becomes 1x to the 0. And of course, x to 0 is just 1. So we get this rule. And the derivative of 1, there are two ways you can think about this. One is, one's a constant. Derivative tells you the rate of change. A constant never changes, so its rate of change is 0. Another way of thinking of this is it's the derivative of 1 is x to the 0 power. So you could think of the power rule as being used here to get 0 times x to the negative 1. Well, that's 0 times 1 over x, which is just 0. So really, these are special cases of the power rule, but almost we don't even think of the power rule when we do them because just the derivative of a constant is 0. So this is true for 1, but it would also be true for 2, 3, pi, whatever. All right. This part down here, the addition, subtraction, and constant multiples. This is all written out, but all this stuff written here makes it look more complicated than it really is. What this says is if you're taking the derivative of a couple of things added together or subtracted, you can just do those derivatives individually. And if you've got a constant times a function, you can just pull the constant out front and then multiply by the derivative. So I've got several examples here, and I'm probably going to draw a few more in because this is worth really drilling on because it's important. So the derivative of 3x to the fourth. This is the 3 is a constant, so it stays out front. So you get 3, then times the derivative of x to the fourth. I'm probably not going to write that step out again because this should become automatic. So it's 3 times 4x to the third, or just 12x cubed. Derivative of 5x squared. Think of this again as taking this 2 and bringing it down front. So 5 times 2 is 10, x to the first power. I'm going to write another example in over here. Derivative of 7x to the fourth is going to be 28x cubed. Excuse me. All right. The other thing is if you've got things added or subtracted together, you can do their derivatives individually. So the derivative of x squared plus x to the fifth is going to be 2x plus 5x to the 4. Derivative of 4 root x. Remember, that's the same as derivative of 4x to the 1/2. So that's 4 times a half x to the minus a half. So that's 2x to the minus 1/2, or 2 over square root of x. All right, a few more special cases to memorize. If you take the derivative of a constant times x, it's just the constant. And if you think about it, that makes good sense because if you take the derivative of mx plus b, I'll go ahead and throw the b in. That's the equation of a line, or it's the expression. I guess it's not an equation because it's mx plus b. It doesn't have y equals on it. But anyway, if you take the derivative of that, the derivative is going to be the slope, which is just m. So the derivative of this is of a constant times x is just the constant. And I mentioned this earlier, the derivative of any constant is 0. So let's do some more of this stuff. Find the derivative of these functions. Right, for this one, f prime x cubed gives me 3x squared. 4x squared gives me 8x. Minus x is, derivative is -1. And the derivative of the constant is 0. I'm going to write it there, but I'm going to erase it because you don't need it. All right, this one below, s of t. S prime of t, derivative of 100 is 0. Derivative of 40t is 40. Derivative of 16t squared is minus 32t. Okay, over here we've got two functions of r. One's the area of a circle. The area of a circle is pi r squared. If we take the derivative of this, the 2 comes down front with the pi. Now remember, pi is a constant. So the 2 hops down front, you get 2 pi, then r to the first power. And for this one, this is a formula for the volume of a sphere. If we take its derivative, we get 3, I'll write this out, times 4/3 pi r to the second, 4 pi r squared. So that's several examples there of derivatives of polynomials. Let's do one more. F of x equals x cubed plus 3x to the 4th minus 9x squared plus 5. Derivative of this thing is going to be 3x squared plus 12x cubed minus 18x plus 0, which I'm not going to write in. All right, let's do a few more complicated examples. This first one, 2x squared plus 5 squared. Now, later we'll learn something called the chain rule that will let us deal with this in a different way. But for now, really the only thing we can do is square this thing out. So if I square it, f of x is 4x to the 4th plus 20x squared plus 25. And notice that's still f, not f prime, because I haven't taken the derivative yet. Now I'm going to take the derivative and get 16x cubed plus 40x. All right. This next one here, we've got a fraction, a rational function. Now, later we'll learn something called the quotient rule that will give us another method for dealing with this. But for right now, what we need to do is split it up. I'm going to split it up into 6x squared over 3x plus 3x over 3x plus 9 over 3x. And now this is going to be, this will reduce, this reduces to just 2x plus 1 plus 9 divided by 3 is 3. I'm going to write this as 3. This last one is 3x to the negative 1. That way I can apply the power rule. Now this is f prime of x. Derivative is going to be 2 plus 0 plus negative 1 times 3x to the minus 2. And I'm going to rewrite this as 2 minus 3 over x squared. That's how I would write it. This is a perfectly acceptable answer. One other thing someone might do though, somebody might take this 2 and multiply it by x squared over x squared and change this into 2x squared minus 3 over x squared. So either one of those are fine. The main reason I throw that second one in there is because sometimes the book does that kind of thing, where they want the answer to be a rational function for whatever reason. So on a test, I would accept either one of these as the correct answer. But if you're doing your homework and you look in the book, you need to be able to recognize that they're the same in case you come up with one and the book gives you the other version. Okay, this one. X squared plus 5 times 3x plus 4. What we have to do here is first FOIL the thing out, then take the derivative. If I FOIL it out, let's see, I get 3x cubed plus 4x squared plus 15x plus 20. Quick double check. Yeah, and so the derivative is 9x squared plus 8x plus 15. All right, this last example I kind of threw in there for, well, just to show we can't do everything yet. This one right here, we can't split this in, well, we could split it into 3 fractions, but we wouldn't know what to do with them. So this is one we can't do yet. This one, we have to wait for the quotient rule. Now, why can we do one a minute ago that had division in it? It's because, let's see, the one up here that we could do, it only had a single term on bottom. So we could split it up and use the power rule on each individual term. Down here, though, we've got more than one term on bottom, and so we can't do this one yet. All right, that's good enough for this video.